In this video, I'll be showing two proofs that the Earth is flat. In the first half, I'll show how there is no curvature on the horizon, even though there are those that claim that lower portions of buildings being blocked from view by the horizon is the result of curvature. The second part of the video is dedicated to showing that the horizon is very thin. It has no depth to it, and that is evidence that the horizon is the product of perspective and cannot be the product of curvature. Okay, let's go. Hi, I just want to talk about videos like this on YouTube where someone zooms in over a patch of water and they actually zoom in on the horizon, which is really cool. But you can see objects past the horizon, whether it be buildings or ships or something, and the lower portions are blocked from view. Well, the average person looks at that and says, wow, that's curvature of the Earth. And, that's understandable. That's what we've all been taught. What I want to show is that it can't be curvature because there's no curvature on the horizontal axis. And what I want to show is that this is perfectly consistent with perspective. This is exactly what we would see. So here we go. Okay, a little something of how perspective works. See the red and the yellow line. The yellow line is your eye height. The red is the ground plane. And the ground angles up. It visually angles up to your eye level. It's on a trajectory. So the way perspective works on a flat plane is that where that intersects, the ground plane and your eye plane intersect, is where the horizon will form, because that's as far as you can see. You know what I mean? The ground comes up like a big wall. It's a big ramp. And when it gets to your eye level, you can't see any further. You cannot see any more ground, or in this case, any more water. You can see beyond it, but the bottom portions of things are blocked from view. So that's the reality of our vision. Wow, look how that water ramps up to your eye level and it forms a wall. Incredible, zooming in on that horizon. Notice the buildings behind it, the lower portion is blocked. That's due to perspective. To explain this illustration briefly, when they say they see curvature when they're looking at the buildings, and they're saying because the lower parts disappear, they're calling that curvature. That would be on the z-axis. That's from our eyes to the horizon and beyond. On the x-axis, these are the two that we're concerned with, the z and the x. The x-axis is the horizon, or our horizontal axis. And the x-axis is the one that we don't see any curvature on. They claim to see it on the z, but they say, oh, you can't see it on the x. Well, you should and you must see it on the x, and yet we do not. Okay, here we are looking over the bay. I have it mocked up here so you can, I have the x, y, and z axis, and I got a line across the horizon. And you'll notice I have a guy over there on the right-hand side of the screen, and he's looking across to the left. So the point of this is that here we are looking across this patch of water, and the guy on the beach here says he sees curvature because the building's way off in the horizon. Once you zoom in, the lower parts disappear, so he's claiming curvature on the z-axis. Yet, we take this guy over here to the right, and let's say he's doing the same exact thing. He's looking across the same patch of water, and he sees buildings off in the distance, and the lower portions disappear, and he's claiming curvature. Now, his z-axis is our x-axis. You see what I'm saying? So what I'm going to do here in a second is I'm going to zoom in on this whole, the zoomed out shot of the horizon, and we're going to scan it from right to left, and we're going to show that there's no curvature on the x-axis. Yet there should be curvature, and there must be curvature on the x-axis, because that would be someone else's z-axis. Like, for instance, if he's looking at our z-axis, that's his horizontal axis, and he should see curvature, because it's a ball, remember? But we don't see that. So here we go. Okay, so on the next slide, I'm going to blow up the slide, and I'm going to zoom into the horizon, and we're going to put a straight line against it, and we're going to scan it from right to left, and we're going to see what it looks like. Let's go. Okay, here we go. Look for any separation between the horizon and the straight yellow line, especially at the beginning of the picture and at the end, or the right side of the picture. That's where they say you'll see curvature. So we look, and we have, I put a little gap between the line and the horizon. And there we go. Looks perfect. Okay, and we're going to maintain that gap all the way across. I can't believe they try to get away with this. They say you can't see curvature, but then they see the building's lower portions disappearing and they yell curvature. But here we are. Here's the horizon. Nice long patch of horizon, and let's look at the end. Perfect. Not an ounce of curvature. Okay, I just want to say a word about zooming in with a telescope. There are people that think that I've spoken to that if you use a telescope, your horizon will be further. The stronger the telescope, the further the horizon will move away from you. Well, that's not the case. The horizon is determined and formed by the ground visually angling up to your eye level. As you see in the beginning of the video here, where he's zooming in across the water, you can see a horizon form, and then as he keeps zooming in, the horizon doesn't get further away. The horizon gets closer, and it gets bigger. He's zooming in on the horizon. That horizon is formed whether you're looking at it with the naked eye or a telescope. All of the telescope allows you to do is to see it larger. See this picture on the top here? If the lines were parallel and perspective wasn't a reality, then yeah, the stronger the telescope, you could just see parallel to the ground. But the fact is, perspective causes the ground to visually angle up. And where that intersects is your horizon, and it's regardless of whether or not you're using a telescope. Concerning the convergence lines that go to your horizon and your eye level, I just want to show you a few slides from my Perspective Horizon Flat Earth video. That the parallel lines do not angle or converge towards the ground, nor do they angle towards the ceiling, nor to the left or right. They angle to the eye level of the observer. This image is a product of our eyes. These are horizontal parallel lines, yet we see them not as parallel, but on an angle towards a point in the distance. Now, of course, we know that they are parallel, but they visually are not. Here you can see parallel lines made up of bricks on the walls. The wall on the left, though, is headed out towards the horizon, and all the lines angle toward the eye level of the observer. The bottom ones angle up and the top ones angle down. This is a great illustration of how all the lines angle to your eye position. You can't deny it. All of the lines converge at a center point on the horizon called the vanishing point. Parallel lines above it angle down, the lines below angle up, the sides angle in. The vanishing point is the intersection of the horizontal and vertical axis of our eye position. It's parallel all the way out, parallel with the ground. That's why I say you can't look down at the horizon, because the horizon angles up to your eye level. The two, your eye level and the ground plane, are parallel all the way to the horizon, but it's the bottom ground plane that angles up to your eye level. Okay, here's a new slide. Here's a guy sitting in the middle of the ocean. You can see the water angles up and on each side of him to our eye level. Actually angles all the way around him. Just like looking down that long hallway, the floor angles up to your eye position, the ceiling angles down, the walls angle in. That's perspective. Here's another one with the guy in the boat. Whether he's in the hallway or out on the ocean, the ground plane angles up to your eye position. And so you can't see any ground past that point once it intersects with your eye height. So items or objects beyond the horizon will be blocked, especially the ground, and then lower portions of objects beyond the horizon will have their bottoms blocked from view. And here's another one. You can see the water ramp up to the eye level, and the building beyond the horizon has its lower portions obscured. It's kind of like putting your thumb out at arm's length and putting it level with your eyes. You can block things much bigger than your thumb. That's due to perspective. And the same happens here. The further away that building is, the more of it gets blocked, starting from the bottom up. Okay, that concludes the first part, dealing with that there's no curvature on the x-axis or the horizontal axis.
Hello guys. After 3 months of investigating on the flat Earth model, I finally found the 100% proof that the Earth is not a globe. And that's how I found it. This video is called Go Fast 2014. You can check out the full video, link is in the description. Basically, this video is a world record for the highest private rocket ever launched into space, and you can see the full flight without any cuts, filmed from 3 onboard cameras. The highest altitude is about 120 kilometers or 73 miles. That's so amazing. I always searched for a video like this. Unfortunately, it appears that the camera have fisheye lenses, however, the Earth still looks flat. I was watching this video at least 100 times and analyzed it frame by frame, hoping to find a proof for either the flat Earth or the globe Earth model. And then it hit me. The moon. You can clearly see the moon in these videos. Would that even be possible if the Earth is a globe? If I check the position of the moon at the date and time the video was taken, and it turns out that the moon would be underneath the curvature, it would prove that the Earth is not a globe. The video was shot on the 14th of July 2014. Unfortunately, I couldn't find the time the rocket was launched, and I would need a time to get the exact position of the moon. So I started investigating to find an approximate time when the rocket was launched. I found this video that was taken a few moments before the rocket was launched.
I did 2 circles around the rocket. Landed safely. Now the next morning I did a short flight just before the rocket launched.
Did you hear what he said? He said the next morning I did a short flight just before the rocket launched. That means the rocket was launched somewhere in the morning. It looks clear, the sun is already out, so it can't be that early in the morning. However, after the launch, they were flying in a helicopter to see where the rocket comes down. For a split second in this video, you can see a GPS device in the helicopter, which shows the time, and the time is 11:40. So the launch must be between approximately 8 o'clock at the morning and 11 AM. The rocket was launched in the Black Rock Desert in Nevada, USA. In July, Nevada's time zone is Pacific Daylight Time, which is UTC -7. Now, let's check out where the moon was at this time. I'm using timeanddate.com and trying to find where the moon was on the 14th of July from 15 o'clock UTC to 18 o'clock UTC. As you can see, by the time the rocket was launched, the moon was in this area, right over Australia. So, if the Earth is a globe, it would be impossible to see the moon from Nevada, because the moon would basically be on the other side of the globe. To imagine this better, there's this website called solarsystemscope.com, and you can also simulate a date and time here, and I also put the right date in. I'm not sure about the time zone here, so I just placed it so the moon would be above Australia, like we saw it on timeanddate.com. So if the Earth is a globe, and if this is our solar system, then tell me, how is it possible to see the moon, which would be here, from Nevada, USA, which is here? It's impossible. So if you say that the Earth is a globe, please tell me how this is possible. That's it for today.